In this video, I'm going to go over some examples from three-dimensional coordinate geometry. Let's start with the first example, plotting the points 2, 4, 7 and -4, 3, -5 in three-dimensional space R3. Let's start with the first point. So we'll draw the coordinate axes. Here's the x-axis, the y-axis, and the z-axis. The point 2, 4, 7, 2 is the x-coordinate, so we go 2 units in the direction of the positive x-axis, 1, 2. Then we go 4 units in the positive y-axis, 1, 2, 3, 4. Notice how I'm going parallel to the y-axis. And we're going to go 7 units in the positive z-axis because 7 is the z-coordinate. So we go 1, 2, 3, 4, 5, 6, 7. And that is the point 2, 4, 7. Next, let's plot the point -4, 3, -5. in three-dimensional space. Let's draw the axes first. Z-axis, x-axis, y-axis. The x-coordinate is -4, so I'm going to have to go -4 or 4 units in the negative x direction. So let's extend the x-axis in the negative direction. So we need to go -4 in that direction, -1, -2, -3, -4. The y-coordinate is 3, so I'm going to have to go 3 units in the positive y direction. So 1, 2, 3. And the z-coordinate is -5, so I'm going to go 5 units in the negative z direction. So the negative z direction is this way. So starting at this point, we're going to go down 1, 2, 3, 4, 5. So think of this point as being below the xy plane. So that is the point -4, 3, -5. Next example, describe and sketch the surfaces represented by the following equations in R3. The equation z equals 3 and the equation y equals 5. Let's start with z equals 3. So, z equals 3 describes all of the points of the form x, y, 3 in R3. In other words, z equals 3 describe all of the points whose z-coordinate is equal to 3. So if we draw that in the xyz space, we get something like this. Here's the z-axis, x-axis, y-axis. What are all of the points whose z-coordinate is 3? Well, these form, altogether, they form the plane that goes through the point 0, 0, 3 and is perpendicular to the z-axis, or in other words, is parallel to the xy plane. So let's draw a plane that goes through this point, 0, 0, 3, and parallel to the xy plane. something like this. This plane is described by the equation z equals 3. Notice, if you pick any point whatsoever in this plane, the x and y could be anything, but it's always true that the z coordinate will always be 3. Next, let's see what the equation y equals 5 in R3 describes. What kind of surface? So we'll say y equals 5 describes points of the form x, 5, and z in R3. In other words, y equals 5 describes all of the points whose y coordinate is 5. This also describes a plane in R3 that goes through the point 0, 5, 0 and is perpendicular to the y-axis. Let's see how that looks. Here are the axes, the z-axis, x-axis, y-axis. So we look at the point 0, 5, 0. X and z are 0 and y is 5. So we go 1, 2, 3, 4, 5. Our plane must go through this point and is going to be perpendicular to the y-axis, or in other words, parallel to the xz plane. So we'll draw something like this. This plane contains the red point 0, 5, 0 and is perpendicular to the y-axis. So this plane has equation y equals 5. Any point you pick in this plane will necessarily have y coordinate 5. Now let's talk about finding the distance between 2 points in R3. So the distance between 2 points P and Q, whose coordinates are x1, y1, z1, and x2, y2, z2 respectively, is the square root of the difference of the x values squared plus the difference of the y values squared plus the difference of the z values squared. Let's see an example that illustrates this equation. Compute the distance between points P 3, minus 1, 5 and Q 2, 8, 0. So the distance between P and Q is the square root of the x-coordinate of Q minus the x-coordinate of P. That's 2 minus 3 squared. Plus the y-coordinate of Q minus the y-coordinate of P. That's 8 minus 1 squared. Plus the z-coordinate of Q minus the z-coordinate of P. That's 0 minus 5 squared. That's equal to the square root of minus 1 squared plus 9 squared. 8 minus 1 is 9. Plus minus 5 squared. That's equal to the square root of 1 plus 81 plus 25, which is equal to the square root of 107. That is the distance between points P and Q. Now let's look at the standard equation of a sphere in R3. For a sphere with center HKL and radius R, the standard equation of that sphere is given by x minus h squared plus y minus k squared plus z minus l squared equals r squared. Let's look at the first example. Find the standard equation of the sphere with center C minus 5 to 11 and radius 14. Let's recall what the standard equation is. X minus h squared plus y minus k squared plus z minus l squared equals r squared. What is h? H is minus 5 plus y minus k, which is 2, plus z minus l, which is 11, equals 14 squared. That's x plus 5 squared plus y minus 2 squared plus z minus 11 squared equals 196. That is the standard equation of the sphere with center minus 5 to 11 and radius 14. Before doing the next example of spheres in R3, I want to do this example to remind you of how to complete the square of a quadratic expression. So let's go over this example. Complete the square for 2x squared minus 6x plus 1. To do that, we first make sure that the coefficient of x squared is 1. In this case, it's not. The coefficient of x squared is 2, so we factor it out. So the first step is to write 2x squared minus 3x plus 1/2. So simply factor out the 2 to make sure that the coefficient of x squared is 1. Now you can see that the coefficient of x squared is 1. Next, we're going to look at the absolute value of the coefficient of x. In other words, we're just going to look at this 3 here. What we do when we complete the square is we take that coefficient, 3, we multiply it by 1/2, that gives 3 over 2, and we square the result. We square 3 over 2 to get 9 over 4. Now I'm going to take that 9 over 4 and add it and subtract it in the appropriate location as follows. So we have 2x squared minus 3x. Now I'm going to add 9 over 4 and subtract 9 over 4 plus 1/2. In essence, I've added 0, so the expression is still really the same. But now what happens, by adding and subtracting this 9 over 4, those 3 terms, x squared minus 3x plus 9 over 4, give us a complete square. So we have 2 x squared minus 3x plus 9 over 4 is equal to x minus 3 over 2 squared. And you can check that this is true by expanding x minus 3 over 2 squared. If you do that, you'll recover your x squared minus 3x plus 9 over 4. We have then minus 9 over 4, and 1/2, let's write it as 2 over 4 to make the denominators the same. We have 2x minus 3 over 2 squared plus minus 7 over 4. Let's distribute the 2 to get 2x minus 3 over 2 squared minus 2 times 7 over 4 is 7 over 2. And that is completing the square. Now let's move on to the next example about spheres. Show that x squared plus y squared plus z squared plus 4x minus 6y plus 2z plus 6 equals 0 describes a sphere in R3. And once we do that, we need to figure out the center and the radius of this sphere. The trick to doing this problem is completing the square. That's why I did the example about completing the square before this example. So we start as follows. I'm going to rearrange the expression and write it as x squared plus 4x plus y squared minus 6y plus z squared plus 2z plus 6 equals 0. In other words, I group all the x's together, all the y's together, and all of the z's together. Now I'm going to complete the square 3 times. I'm going to do it once for the quadratic expression in x, once for the quadratic expression in y, and once for the quadratic expression in z. Now remember, the first step in completing the square is making sure that the coefficient, the squared coefficient, is a 1. It is 1 in all of these cases for x, y, and z, so we don't have to follow the first step. It's already done for us. Now I'm going to take the coefficient of x, namely 4. I'm going to multiply it by 1/2 and square the result. So let's go here. If we look at 4, we multiply it by 1/2, that gives us 2. Square the result gives us 4 again. So we have x squared plus 4x. We're going to add 4 and subtract 4. Plus y squared minus 6y. I'm going to look at 6, multiplied by 1/2 to get 3, and square the result to get 9. So I'm going to add 9 and subtract 9. Plus z squared plus 2z. I'm going to look at 2, multiply by 1/2 to get 1, and square the result to get 1. So I'm going to add 1 and subtract 1. Plus 6 equals 0. Because we completed the square, x squared plus 4x plus 4 is going to give us a complete square. Y squared minus 6 plus 9 is going to give us a complete square. And z squared plus 2z plus 1 is going to give us a complete square. So that's equal to x plus 2 squared. This is equal to x squared plus 4x plus 4 minus 4 plus y squared minus 6x plus 9. That's equal to y minus 3 squared. We have minus 9 plus z squared plus 2z plus 1, that's z plus 1 squared, minus 1 plus 6 equals 0. That's equal to x plus 2 squared plus y minus 3 squared plus z plus 1 squared equals minus 4 minus 9 is minus 13, minus 1, that's minus 14, plus 6, that's minus 8. If we move it to the right-hand side, that's equal to 8. But now, this is the standard equation. This is the standard equation of the sphere with center -2, 3, -1, and radius square root of 8, which can be written as 2 root 2. So by completing the square, we got the standard equation of the sphere. And by looking at the standard equation, we can extract the radius and the center. Final example. Describe the trace of the sphere x minus 2 squared plus y minus 4 squared plus z minus 5 squared equals 34 in the xy plane. Now, since the sphere is a two-dimensional surface and the xy plane is a two-dimensional surface, the trace, which is the intersection of both surfaces, is going to be a one-dimensional curve. So we'd write the trace is a one-dimensional curve which belongs to both the sphere and the plane. Now the sphere is already given to us. Let's recall what the equation of the xy plane is. The xy plane has equation z equals 0. That is because any point in the xy plane has z coordinate 0. And as far as the sphere is concerned, let's rewrite the equation. It has equation x minus 2 squared plus y minus 4 squared plus z minus 5 squared equals 34. To find the intersection or the trace of the sphere and the xy plane, we simply look at z equals 0 from the equation of the xy plane and plug it in for z in the equation of the sphere. If we do that, we get the following. X minus 2 squared plus y minus 4 squared plus 0 minus 5 squared equals 34. That's x minus 2 squared plus y minus 4 squared plus 25 equals 34. That's x minus 2 squared plus y minus 4 squared equals 34 minus 25, which is 9. So we have two equations that determine the trace. First, the equation z equal 0, and the second equation is x minus 2 squared plus y minus 4 squared equals 9. Okay? Let's rewrite that. So the trace is determined by the following two equations: z equals 0 and x minus 2 squared plus y minus 4 squared equals 9. Together, this trace describes the circle sitting in the xy plane. This is coming from z equals 0. So the circle sitting in the xy plane with radius 3 and center 2, 4, 0. Again, so the trace is the circle with radius square root of 9, which is 3, and center, the x-coordinate of the center is 2, the y-coordinate is 4, and the z-coordinate is 0. So the center is 2, 4, 0. Since the z-coordinate is 0, notice how the circle sits in the xy plane. So that is the trace of the sphere x minus 2 squared plus y minus 4 squared plus z minus 5 squared equals 34 in the xy plane.